Hello, welcome to the next part of your redox reaction. Now we can discuss the remaining part, that is rules for finding oxidation state. So moving to the third rule. In periodic table, and you should have some kind of idea about the oxidation state in periodic table. In periodic table, we have the group 1, like alkali metals. The elements are like lithium, sodium, potassium, rubidium, cesium. And they all shows a +1 oxidation state always. What about the group 2? The group 2 members, beryllium, magnesium, calcium, strontium, barium. And they all can show +2 always. Group 3. The group 3 means it is 13th group. It means 13th. Because the actual group 3 is a transition, right? Transition element, right? So from group 3 to group 12, it is transition element, right? They can show variable oxidation state. So we can't predict the fixed one. So simply group 3 means it is group 13. And you know the members of group 13: boron, aluminium, gallium, indium, thallium. Okay. So there is not a fixed oxidation state. They can vary its oxidation state from -1 to +3. -1 to +3. Okay. But there is, in the case of your aluminium, it only shows +3. That is a fixed one. Aluminium can only show +3 oxidation state. Ready? Similarly, moving to the next, that is group 4. Group 4 means group 14. Okay. Members are carbon, silicon, germanium, tin, lead. And the range of their variation is from -4 to +4. Oh, so huge variation, -4 to +4. And there is no fixed one. Okay. Group 5. Group 5, the members are nitrogen, phosphorus, arsenic, antimony, bismuth. And they can show the variation from -3 to +5. And the group 6. Group 6. Group 6 means 16th one. Oxygen, sulfur, selenium, tellurium. And they shows from -2 to +6. And the well familiar halogen, group 7, group 17. Fluorine, chlorine, bromine, iodine. And the variation from -1 to +7. But in the case of fluorine, it only shows -1 oxidation state. It only shows -1 oxidation state. And what about group 8? Group 8 means 18th group. And I think you know that in group 8, xenon, radon, krypton can show compounds, not by helium, neon, argon. And they can show +2, +4, +6, +8, so on. I think you are familiar with the XeF2, XeF4, XeF6, and XeF8 or XeO4. It's not F8, XeO4. Okay. So the oxidation states are like +2, +4, +6, +8. So you should by heart this. Okay, you should by heart this. It is a compulsory one. This is the most important one. Round table, you should by heart it. Okay, that is always fixed. And in a normal case, normally you should choose oxygen with an oxidation state of -2. Normally you have to choose the oxidation state of oxygen as -2 and oxidation state of halogen as -1 normally, in a normal sense, without any exception. And the whole charge of SO3 as -2, the whole charge of SO4 as -2, the whole charge of NO2 as -1, the whole charge of NO3 as -1, the whole charge of CO3 as -2, the whole charge of OH as -1. Wait, the whole charge of PO4 as -3, the whole charge of OH as -1. OH means like this. OH is -1. OOH is also -1. What do you mean by OOH? It's a peroxy linkage. OOH, it should be -1. Okay. OK, oxygen with potassium, it's also -1. The whole charge of OK is -1. The whole charge of OCl is also -1. The whole charge of ONA is also -1. Okay. That means that if you are given a compound Fe2O3 and you are asked to find the oxidation state of iron. So you are familiar with the oxidation state of oxygen, right? If you are asked to find the oxidation state of iron, which means that you should know the oxidation state of oxygen and then you choose it as -2. That is the logic. If oxygen is not to you, then you choose it as -2. Okay, but here, if you have Na2O2, and you're asked to find the oxidation state of oxygen, then you are not supposed to write it as -2. Okay, it is not -2. If you are asked to find the oxidation state of oxygen, then you have to find it. Okay, otherwise, in some question it is clear that you know the oxidation state of oxygen and you are asked to find its companion's oxidation state, then you choose oxidation state of oxygen as -2, like that. If you know the oxidation state of chlorine, if the underlined one is iron, find the oxidation state of iron, Fe, which means that you know the oxidation state of chlorine, right? Okay, at a time only one unknown is there, right? I think you're familiar with that. So if you ask to find the oxidation state of Fe and they tell you that you know the oxidation state of chlorine, then chlorine means it's an halogen, then you have to choose -1. Here you have to choose -1. But in the case of Cl2O7, they underlined chlorine, which means they are asked to find the oxidation state of chlorine. Then you are not supposed to write it as -1 because it is not -1. Then you have to find it using the oxygen or the companion. Ready? That's the idea. It will be discussed more in detail. Okay. So this is the idea about the periodic table, oxidation state of elements in periodic table. Moving to the next idea. The next idea that is okay. Listen. In the case of metal amalgams and metal carbonyls, what it is? Metal amalgams and metal carbonyls. Okay. I think you are familiar with the metal amalgam. Okay. And that's all about the third rule. In metal amalgam means any solid metal with or dissolved in mercury. Or in metal carbonyls. And you know that metal carbonyls, some compounds which you studied in your coordination compounds, a synergic effect, back bonding. What are the examples of metal amalgam? We have sodium amalgam, zinc amalgam, like that. Okay. And in case of metal amalgam and in metal carbonyls, the OS of metal, the oxidation state of metal is 0. The oxidation state of metal is 0. So here the oxidation state of sodium, it is OS is 0. The oxidation state of zinc, that is also 0. Okay. So in the case of amalgams, their oxidation state will be 0. That's a typical knot point. You have to know that, okay? What about the metal carbonyls? Examples of metal carbonyls? I think you are familiar with the nickel tetracarbonyl Mons process of your metallurgy, right? And iron pentacarbonyl FeCO5 and chromium hexacarbonyl CrCO5, CrCO6 times, it's not 5. And these all are metal carbonyls, nickel tetracarbonyl, iron pentacarbonyl, chromium hexacarbonyl, where the oxidation state of your metal will be 0. That's the next point. I have to remember, okay? Moving to the next idea. Highest OS in periodic table. Highest OS in periodic table by osmium and ruthenium. Highest OS in periodic table is shown by osmium and ruthenium. What are they? In osmium can show OSO4, osmium tetroxide, and ruthenium also can show ruthenium tetroxide, where their oxidation state is the maximum plus 8 and maximum plus 8. So these are the two elements which can show maximum of plus 8 oxidation state. This is the maximum limit of an element or the maximum limit of oxidation state of an element, okay? Next point. In case of hydrogen, in the case of hydrogen, for hydrogen, the element hydrogen can show 3 different oxidation state. The one is discussed. In H2, the oxidation state of hydrogen is 0, right? But if the hydrogen is with the metal, if your hydrogen is combined with the metal, then the oxidation state of hydrogen will be -1. That means you know that it exists as H minus, hydride ion. For example, if I have magnesium hydride, MgH2, what about the oxidation state of hydrogen? It should be -1. Or if your hydrogen with the non-metal, fine. If your hydrogen with the non-metal or in acid, like hydrogen can exist in acid, right? Yeah. If a hydrogen with a non-metal or in which is in an acid, then it will be in a H plus oxidation or H plus form. That means it will be in a +1 oxidation state. For example, in ammonia, your hydrogen is combined with an hydrogen non-metal. Then what about the oxidation state of hydrogen? It will be +1. Another example, in sulfuric acid, your hydrogen is combined or your hydrogen is in an acid form. So hydrogen which exists in H plus. Ready? Okay. Now you should familiar the OS of oxygen. The different variable oxidation state shown by oxygen. Oxygen can show different varieties, and the most common one is oxide, O2 minus. That is already discussed. Okay. So the next point is oxidation state of oxygen. Listen. The common oxidation state, that is the first one. And the ion is said to be the oxygen in the common oxidation state, that is, -2. The ion is known as oxide ion, and it will be in the form of O2 minus. For example, Na2O. This is said to be, or simply leave it, K2O. This is said to be potassium oxide. Potassium oxide. Okay. So the OS here is -2. -2. Okay. Moving to the next. This is the first one. The second one. This is the first one. The second one is peroxide. What it is? Peroxide. Peroxide is something like this. O2 to minus. O2 to minus. Where the oxidation state is -1. Because two oxygen have -2 oxidation. Two oxygen have -2 charge, which means each oxygen should possess -1. So oxidation state is, here it is, in oxide it is -2, in peroxide it is -1. Okay, for example, if I have a compound like this, K2O2, then it is said to be potassium peroxide. Move to the next category, that is superoxide. Superoxide. How it will look like means O2 minus. Two oxygen have a negative charge, which means each oxygen have, two oxygen have a single negative charge, which means each oxygen have a negative half, right? Okay, for example, KO2. So KO2 is called as potassium superoxide, whereas K2O2 is potassium peroxide, whereas K2O is potassium oxide. Okay, and there are more and more different varieties. The next variety is, there is oxygen with rubidium. It can show a typical compound RbO3. Where in RbO3, Rb is in +1, no doubt, because it is an alkali metal, strong alkali metal. So it can only drop one electron. So it can exist in a +1 oxidation state. Whereas in the case of oxygen, it should be -1 because the charge will be equal and opposite. So 3 oxygen should carry -1, which means the oxidation state per head means per head will be -1/3. -1/3. Okay. The next category in O2. O2 is a diatomic form of oxygen. The oxidation state is 0, right? The oxidation state is 0. And the next, something positive oxidation state. O2 PtF6. O2 PtF6. That is a typical compound where the PtF6 have a negative charge and O2 have a positive charge. O2 plus. Oxygenyl ion. The ion is known as oxygenyl ion. Okay, 2 oxygen have a positive charge. Then what about the oxidation state of each oxygen? It will be +1/2. Agreed? So this is the next possible variation of oxygen. Moving to the next. Dioxane difluoride, O2F2. Dioxane difluoride, O2F2. You know that fluorine can offer a -1 oxidation state always. So 2 fluorine -2. So here the oxygen is in +2 oxidation state. So 2 oxygen is in +2 oxidation state, which means each oxygen have +2 for 2 oxygen. So each one have +1, right? Dioxane difluoride. Another compound where the oxygen exists in a +1 oxidation or positive oxidation state is OF2, oxygen difluoride. So 2 fluorine offer -2, then your oxygen should offer +2. So the oxidation state of your oxygen is +2, right? So these all are the different, but the typical oxidation state shown by your oxygen. Okay, keep that. Ready? Moving to the next logic, or moving to the next idea. If you are given with a compound, which contains carbon, hydrogen and oxygen, there are number of carbons, number of oxygen and number of hydrogen, not in 1:1 ratio. Okay, there is no it doesn't mean that there is 1 carbon, 1 hydrogen, 1 oxygen, not like that. You are given with a compound. Listen, oxidation or average oxidation state of carbon, in a compound CN or in a compound CX, HY, OZ, which means some number of carbon, some number of hydrogen, some number of oxygen, like that. Okay. Then, so what is the logic? You are asked to find the average oxidation state of carbon in a compound which contains X number of carbon and Y number of hydrogen and Z number of oxygen. Average oxidation state. What do you mean by the sense average? Average means the total oxidation state of carbon divided by total number of carbon. Okay, total oxidation state of carbon divided by total number of carbon. And it can be easily calculated using the equation. The equation is twice the number of oxygen minus number of hydrogen divided by number of carbon. This is the formula for finding average oxygen state of carbon where the molecule have carbon, hydrogen and oxygen. Okay, twice the number of oxygen. What it is? NO, number of oxygen. And what do you mean by NH? Number of hydrogen. And what about NC? Number of carbon. So twice the number of hydrogen minus, number of oxygen minus number of hydrogen divided by number of carbon. I'll give you a lot of examples. Okay, your first molecule is acetic acid. So you're asked to find the oxygen state of carbon in acetic acid. Simply, if you're asked to find the oxygen state of carbon, means it will be the average oxygen state. And you can write your acetic acid as C2H4O2, right? Okay, so what will be the formula? Twice the number of carbon, so twice the number of oxygen, 2 into 2, minus number of hydrogen, that means 4, divided by number of carbon. So the top will be 0, so the average oxygen state of carbon will be 0. The next molecule is acetaldehyde, and you can write it as C2H4O, right? Yeah, C2H4O. So what about the formula? Twice the number of oxygen, 2 into 1, right? Here is 1, minus number of hydrogen divided by number of carbon. So it will be minus 2 divided by 2. So the total or the average oxygen state of carbon will be minus 1. The next, that is for your well familiar monosaccharide C2, C6H12O6. What about the average oxygen state of carbon? Twice the number of oxygen minus number of hydrogen divided by number of carbon. 2 into 6 minus 12 divided by 6. And it will be 0. What about sucrose formula or disaccharide formula C12H22O11? Tell me. Twice the number of oxygen, 2 into 11, minus number of hydrogen, 22, divided by number of carbon is also 0. Oh, fine. Okay. Ready? And it is not necessary that the compound should have carbon, hydrogen and oxygen. It either have carbon and oxygen or have carbon and hydrogen. It is simply carbon and one of oxygen or hydrogen is enough. Wait, we have carbon dioxide. Here there is no hydrogen, right? But we can use the formula. Twice the number of oxygen, 2 into 2, minus number of hydrogen, that is 0 because hydrogen is absent, divided by number of carbon. Carbon is 1, right? So what will be the formula? Plus 4. And we have another compound, CH4. CH4. Tell me. Twice the number of oxygen. Oxygen is 0. Minus number of hydrogen, that is 4. Divided by 1. That will be the answer will be minus 4. And we have propane. You are given the propane. You are asked to find the average oxygen state of. Simply you are asked to find the oxygen state of carbon. So twice the number of oxygen, that is 0, minus number of hydrogen, that is minus 8, divided by 3. So the answer is minus 8 by 3. So this is a somewhat useful formula. Okay. So keep it in mind. Ready? Moving to the next rule. That is something about the covalent bond treatment. Covalent bond treatment. Look at that. Discuss. Guys, and now we want to analyze how a covalent bond is treated in terms of oxidation state. Okay, listen, you know what is a covalent bond. Okay, if I have a covalent bond like this, A to B, there is a covalent bond from A to B. Okay, A to B. Well, A less electronegative. A is less electronegative, but B is more electronegative. If A is less electronegative, then relatively B will be more electronegative because A and B are entirely different. Okay. Then listen. So it is clear that the polarization of bond towards B or the electron pair is little bit attracted by your B, right? So electron density moving towards B because B is more electronegative than A. If so, your B having a charge of or B should have a charge of -1, or B should assume a charge of -1, because somewhat electron is gained by B, like that, okay? And A having a charge of +1. A having a charge of +1. Ready? Okay. That is a concept. Okay. If the very same two atoms have a double bond, means A and B have a double bond, then your treatment based on this oxidation state is, for this bond, electron density towards B. For this bond also, electron density towards B. So your B having a -2 charge and A having a +2 charge, right? B having a -2 charge and A having a +2 charge. Because there are two bonds. Each have -1, -1, +1, +1. So total -2, +2. Like that. One more possibility is between A and B, triple bond is also possible. Triple covalent bond is also possible. Then for each bond -1, -1, -1, which means -3, here +3. And this is the logic. Okay. And one more thing is, listen, one more thing is, if there is a covalent bond between two same atoms, okay, then what is the difference? Here, both A and this A are attracted in same force, right? Because they both have same electronegativity. Then the polarization will be 0, 0. Okay, 0, 0. Ready? So simply, this is the logic. If there is a bond, okay, and simply you check which one is more electronegative, then the electron density more closest or more moving towards that electronegative atom. So that electronegative atom assumed to have a -1 charge, and the electropositive atom have a +1 charge or unit positive charge. Okay, like this. This is very important. I'll give you the applications. Before that, you simply know the electronegativity of non-metals. So listen, electronegativity, you have to know this much order. Electronegativity order based on Pauling scale value. Okay, the most electronegative atom is fluorine, followed by oxygen, followed by chlorine, followed by nitrogen, then bromine, then iodine, then sulfur, then carbon, then hydrogen. It is very important. Okay. Ready? Then I'll give you examples. Listen. We can do some examples based on this. Okay. If I have methane, or simply I'm considering the oxidation state of carbon in methane and oxidation state of carbon in CCl4. Both have same geometrical pattern, but let us check what is the difference. This is your methane, right? Yeah, methane. So what about the electron density difference? Carbon and hydrogen. So carbon have more electronegativity. So polarization like this, right? -1, -1, -1, -1. I'm sorry, I'm really sorry. +1, +1, because electron density towards carbon. So this bond have +1 here, -1 here, +1 here, -1 here, +1 here, -1 here, +1 here, -1 here. So total 4 -1, so it will be -4. Agreed? Yeah. What about CCl4? CCl4. Cl, 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 Cl. Okay? Tell me. Tell me, which one has greater electronegativity? Here the carbon, here the chlorine. Chlorine have comparatively much more electronegativity than carbon. So the polarization towards chlorine like this, like this, like this, like this. So for this bond, chlorine attains -1 and carbon attains +1. For this one, chlorine -1. For this one, chlorine -1. For this one, chlorine -1. So +1, +1, +1, +1 from both of all four sides. So the total will be +4. So here the carbon is -4, here the carbon is +4. See the difference? Okay, because the oxidation state of carbon varies in accordance to the electronegativity difference. Okay, here the less electronegative hydrogen occurs. So the -4 have to attain by carbon, but here more electronegative chlorine occur. Okay, so carbon should tend to oppose the polarity. Ready? So I think you're okay with that. Okay, let's do some more problems or some more case. Listen. Already in the previous section we discussed that ethanoic acid, right? Ethanoic acid, CH3 COH, which means C2H4O2. Yeah, twice the number of oxygen minus number of hydrogen divided by number of carbon. Discuss the average OS of carbon equal to 0. Right? We know that from that formula. Okay. Now we can check the whole means now we can check the oxidation state of all elements in this acetic acid. Okay, for that your acetic acid is something like this in an elaborated version. CH3 C double bond OH, right? Is it okay? Yeah. Listen carefully. Listen carefully. First of all, I am here. So this is an H. This is also an H. So electronegativity difference. Hydrogen less electronegative than carbon. So electron density towards carbon. Here the carbon, but it is surrounded by the very same carbon. So carbon surrounded by carbon, there is no problem. So there is no polarization here, right? There is no polarization here. Is it okay? Yeah. So no polarization. This bond have no issue here. So +1, +1. So this carbon have to supply -3. Okay. What about this carbon? Tell me. This carbon is surrounded by oxygen, where electronegativity towards the, and this is surrounded by another oxygen in a 2 bond, electron density towards the. So this have -2, this have -1. Ready? From here, there is no problem. For this carbon, from the left side, there is no problem because it is surrounded by carbon itself. So -1, -2, -3. So this carbon have to apply, or this carbon have to supply +3. Ready? This carbon have to supply -3, but this have to supply +3. Now what about this bond? What about the oxidation state of oxygen? Let's check. This bond electronegativity towards oxygen. So oxygen have -1 and hydrogen have +1. So the total oxidation state of oxygen is -1 from OH bond and -1 from CO bond. Okay, whatever it may be, average OS of carbon. Average OS of carbon. How you obtain average OS? Total oxidation state -3 from this carbon +3 from another carbon divided by total number of carbon. There are 2 carbons, okay? So the answer is 0. It is already obtained from the formula. Okay. Ready? But from the formula, you obtain the what do you obtain? From the formula, you obtain the total oxidation state divided by total number of atom, average. Okay. From by this method, you obtain the each and every oxidation state of each and every carbons like this. Ready? Let's check formaldehyde. Formaldehyde. Okay. Make it speed. HC double bond OH. This is formaldehyde. Ready? Okay. Tell me. This is a carbon and this bond to here. Electron. Sorry. Here the electron density to carbon from hydrogen. Here from this hydrogen also towards carbon. But from this oxygen, it is towards oxygen. Okay. So here +1. Here +1. Here -2. What about the carbon? Okay, the carbon is surrounded by +1, +1, +2 and -2. Carbon is surrounded by 0. So carbon have to supply 0 charge. Is it okay? If carbon is surrounded by -2 charge, then carbon have to supply +2. If carbon is surrounded by +2 charge, then carbon have to supply -2. If the carbon is surrounded by 0, right? From here +1 and from the -2, so the total is 0. So carbon have to supply 0. Ready? Okay. Listen. We have formaldehyde with, acetaldehyde. Acetaldehyde. This is acetaldehyde. What about the case of acetaldehyde? See. Like this, right? Yeah. Tell me about this carbon. Electron density towards carbon, because, here, +1, +1, +1. For this carbon, from the right side of carbon, for this carbon, from the right side, there is no problem because it is carbon itself, right? So this carbon surrounded by 3 positive charges. So this carbon have to supply -3. Is it okay? Yeah. What about this carbon? To the top, to oxygen. Ready? So oxygen is in -2. To the right, the bond towards carbon. It's not like this because here the bond towards, or here the polarization, electron density towards oxygen. Why? This is more electronegative, but here it is towards hydrogen because hydrogen is less electronegative than carbon. Is it okay? Yes. So here the +1. And for this carbon, from the left side, it is carbon itself. So there is no problem. So in top -2, here +1. So totally a -1 charge is excess. So carbon have to offer +1. Okay. Then what about the average OS? Average OS is the total OS -3 +1 divided by total number. That means -1. -1 will be the average OS. Okay. And when you say -1, you obtain from the formula twice the number of oxygen minus number of hydrogen divided by number of carbon. Okay. Ready? Let's we have hydrocarbon like this. C3H8. I think we obtained the average oxidation state of C3H8 as -8/3. Okay, let's check how it become -8/3. Propane. So let me draw propane. This is your propane. It's very easy. Okay. Propane. All carbon surrounded by either a carbon or hydrogen. And from concern with respect to hydrogen, the electron density is something like this. So +1, +1, +1, and from the no problem. So 3 positive charges. So carbon have to supply -3. From this carbon, electron density like this. So hydrogen +1, +1. For this carbon from the right, there is no problem. From the left, there is also no problem. So surrounded by 2 positive charges, +1, +1. So it have to offer -2. For this carbon, yeah, a bond polarization like this. So +1, +1, +1. From the left, there is no problem. So total surrounded by +3 charge. So here, -3. So the average OS, right? Average OS is -3, -2, -3 divided by 3. That is -8/3. That is we already get. Okay. Ready? I'll give you one more example. Let's check sulfuric acid. H2SO4. H2SO4. Then for this consideration, you have to know the structure of all molecule. Okay. So this is sulfuric acid. 2 oxo linkage and 2 OH bond. Okay. Now check the oxidation state of sulfur. Considering the sulfur, each sulfur surrounded by O. All sulfur surrounded by oxide. So electron density towards oxygen, right? So for this is a single bond, so oxygen is in -1. This is a double bond, oxygen -2. This is a single bond, here -1. This is a double bond, -2. So sulfur surrounded by -2, -1, -2, -1, -6. So sulfur have to offer +6. Okay. So this is the kind of analysis using electronegativity difference in a covalent bond. Now listen. Let's check how a coordinate bond is treated in terms of polarization or in terms of electronegativity. Listen. A coordinate bond. A coordinate bond is a bond or something like a covalent bond, but the electron pair is completely dominated by one atom, right? I think you are familiar with that. Okay. So we have a coordinate bond like this. A coordinate bond from A to B. A coordinate bond from A to B. The condition is that A more electronegative. Listen. A more electronegative. Relatively. Less electronegative is your B. So there is a coordinate bond. There is a coordinate bond. Listen carefully. There is a coordinate bond from a more electronegative atom to less electronegative atom. There is a coordinate bond from more electronegative atom to less electronegative atom. Then there is no problem for that bond. You simply ignore the polarization of that bond. If it is a coordinate bond from more electronegative atom to less electronegative atom, you simply ignore it, which means the charge of these two are 0. Or the polarization of that bond is 0. Simply you ignore it. Okay. If and only if it is from more electronegative to less electronegative. More electronegative to less electronegative. At the very same time, if there is a coordinate bond from X to Y, the condition is that as X is less electronegative, whereas Y is more electronegative. X is less electronegative and Y is more electronegative. Then what about the polarization mean? If there is a coordinate bond from less electronegative to more electronegative, then less electronegative have +2 charge and more electronegative have -2 charge. It's not +1 -1. It is +2 -2 because this is a coordinate bond means you know what is a coordinate bond. And A and B is here. A is an electron rich species and B is the electron deficient species. If this two electron is shared, the two electron from this donor A is ready to share between A and B, then there forms a coordinate bond. The two electrons between the two electrons from the donor A, and he is willing to share that two electrons between A and B to form a covalent like bond, then that bond is said to be coordinate bond line. Then there forms a coordinate bond AB, right? Like this. But these two electrons are from your A. So it is simply represented like this, right? Yeah. So this is a coordinate bond. You know what is a coordinate bond. Okay. So a coordinate bond were from more electronegative to less electronegative. No need of considering it. Okay. No need of considering that bond. But it is from less electronegative to more electronegative. Then your less electronegative have a loss of 2 electrons. It's not 1, 2. Keep in mind. Okay. So plus 2, and the more electronegative have a gain of 2 electrons. So minus 2. Okay. Let me give some examples regarding this. Okay. And your first question, find OS of carbon, hydrogen and nitrogen in hydrogen cyanide and hydrogen isocyanide. Hydrogen cyanide and hydrogen isocyanide. In the case of hydrogen cyanide, there is no problem. It is a covalent molecule. But in the case of hydrogen isocyanide, it is not only a covalent, but also a coordinate bond is there from nitrogen to carbon. Whatever it may be, first of all, we can discuss or we can check the oxidation state of each atom in hydrogen cyanide. Okay, usual logic. This is all are covalent bonds. So what about the polarization of this bond between carbon and hydrogen, where carbon is more electronegative? So electron density towards carbon. So carbon have a -1 charge, where hydrogen have +1 charge, right? Yeah. What about this bond between carbon and hydrogen? Triple bond, fine. And the electronegativity towards nitrogen. So nitrogen have 3 bonds towards it. Okay, so -3. So carbon have +3. So what about the oxidation state of each atom? Hydrogen is in now +1 oxidation state. Carbon is in -1 from here and +3 from there. Then what is the net? What is the net one? Final one, -1 +3. The answer will be +2, right? Yeah. Nitrogen -3. Is it okay? Yeah. So this is oxidation states in hydrogen cyanide. In hydrogen cyanide, whatever it may be. Let's check hydrogen isocyanide. Fine. So first of all, this bond, H and N bond. Nitrogen is more electronegative, no doubt. So electron density towards nitrogen. So nitrogen have a +1 charge, attain a +1 charge, and hydrogen have, nitrogen attain a -1 charge from that covalent bond, and hydrogen have a +1, right? What about this? Noku, listen. It's a coordinate bond from nitrogen to carbon. I think nitrogen is more electronegative, right? Carbon is less electronegative. Is it? Yeah. So no need of considering this one. That's the point. From more electronegative to less electronegative, there is no need of considering that coordinate bond. So you simply leave this coordinate bond as 0, 0. Then there is 2 covalent bond, right? Yeah. Where nitrogen is more electronegative. Nitrogen is more electronegative. And there is 2 covalent bond. So nitrogen from that 2 covalent bond -2. So carbon +2. And you drop this coordinate bond because it is from more electronegative nitrogen to less electronegative carbon. Fine. What about the oxidation state of hydrogen? Yeah. +1. Nitrogen -1 from here, -2 from here. Yeah, -3. Carbon +2 only. Listen. These two are same, right? Yeah. The oxidation state of hydrogen +1 and carbon +2 and hydrogen -3 in hydrogen cyanide and hydrogen isocyanide. But their bonding style and all things are entirely different. Even though their oxidation states are very same. Okay. So I'll give you one more example. Okay. This is an example for the coordinate bond from more electronegative to less electronegative. Agreed. But I'll give you example for less electronegative to more electronegative. Less electronegative to more electronegative. Okay. Let us check NO3 minus nitrate ion. Nitrate ion. Fine. Nitrate ion. Nitrate ion is NO3 minus, right? Yeah. And we know that the oxidation state of nitrogen in nitrate is +5. Okay, or we can check it. Nitrate ion having a structure something like this. And there is nitrogen surrounded by 3 oxygen, and the 3 oxygen are entirely different. Okay, one is a double covalent bond oxygen, one is a single bond covalent or minus, and one is towards one is nothing but it's a coordinate bond. Fine. So first of all, treat this covalent bond. The electron, which one is more electronegative, nitrogen or oxygen? No doubt, it is oxygen. Oxygen is the second most element, electronegative element. So towards oxygen, so oxygen half -2, right? Oxygen half -2. So here nitrogen +2. For this bond, oxygen -2, nitrogen +2. What about this bond? Yeah, very same. Oxygen towards oxygen, so oxygen half -1. So nitrogen half +1. What about here? Yeah, this is a coordinate bond. This is a coordinate bond. Yeah, tell me. A coordinate bond from nitrogen to oxygen. Nitrogen less electronegative. Oxygen more electronegative. Then what is the case? A coordinate bond from less electronegative to more electronegative. Then the less electronegative have a +2 charge and more electronegative have a -2 charge. Fine. So tell me. Yeah. Less electronegative nitrogen have a +2 charge and more electronegative oxygen have a -2 charge. So what is the total charge of nitrogen? +2 +2 +1. That is means nitrogen is in a +5 oxidation state. Okay. So this is a case where the coordinate bond have +2 -2 polarization, and the previous case is the coordinate bond without charge conservation. So there are two chances. A coordinate bond may be from more electronegative to less electronegative, or less electronegative to more electronegative. Okay. Depends on the condition. You have to choose that. Okay. You have to choose that polarization of that bond. Ready? It's very important. For this all kind of analysis of each and every bond, you have to know the electronegativity, relative electronegativity between them. Okay. So the top is fluorine, then oxygen, then chlorine, then nitrogen, then bromine, then iodine, then sulfur, then carbon, then hydrogen. It is very important. It is very important. Okay. That logic is very important. So moving to the last two rules. Moving to the last two rules, or rules for finding oxidation state. Simply I'm entering to the last two rules. Listen carefully. Sum of oxidation state of a neutral molecule is 0. Sum of oxidation state of a neutral molecule is 0. We have a molecule where the charge is 0, which means that each component having a charge where the sum will be 0, right? I'll give you an example. You know this concept, okay? I have a molecule A2B3C4 where the oxidation state of A is +X, oxidation state of B is -Y, oxidation state of Z is +Z, B is +Z, oxidation state of C is -Z. Then how we can apply this concept? This is a neutral molecule, but this is a neutral molecule which consists of 3 atoms, A, B, C, where A having a charge of +X, B having a charge of +Y, C having a charge of -Z. But since it is a neutral molecule, the sum of the whole charge will be 0. And how we can apply that concept? First, the first atom, which it is? A. So its oxidation state +X into its number 2. So the total charge of A is over. Then plus. Moving to the next species, that is B. What is its charge? +Y. +Y. Okay. +Y. Yeah. And the charge of B is +Y. But the total charge, to get total charge, we have to multiply its number, right? The number is 3. Plus move to the next. It is Z. The charge of Z is minus, but the total is 4. And this is the sum of all charges of A, B, C. And the charge will be, the sum will be 0. Okay. So 2x plus 3y minus 4z. That is 0 here. Okay. 2x plus 3y minus 4z is 0 here. Is it okay? Yes. So this is a point. The sum of oxidation state of all atoms in a molecule will be 0. Okay. Ready? Using this idea, we can find the oxidation state of any elements. Let's find the oxidation state of Mn in KMnO4. Mn in KMnO4. There are two methods. Okay. You have to know both. Method number 1, usual method. Take your KMnO4. Okay. And unknown is Mn, right? Put its oxidation state as X. Then it is a neutral molecule, right? This is a neutral molecule. KMnO4 is a neutral molecule. Agreed? Because for a neutral molecule, there is no charge mentioned here, right? Yeah. So this is a neutral molecule. So sum of its oxidation state will be 0. So using that concept, the first species, that is potassium, having an oxidation state +1. That you have to know because potassium is a first group element that I already discussed. First group element having an oxidation state of +1. It is discussed. So +1 into number of potassium 1. So it is over. Then oxidation state of manganese, put it as X into number of manganese, that is 1, plus oxidation state of oxygen, that is -2. That you have to know. Already told you that. If you consider the oxidation state of oxygen, as you know, or if they mean that you know the oxidation state of oxygen, then you have to choose -2. So -2 into 4, which is equal to 0. So +1 plus x minus 8 equal to 0. So x is equal to +7, right? Yeah. This is one of the method for finding the oxidation state of KMnO4. The usual method, I think you know that. Okay. The second method, it is in a simple idea. Split this whole. Okay, so oxygen -2 into 4, -8. So O4 part offers -8. Potassium +1 into 1, +1. So K part offer +1. In order to become the whole 0, or what about the sum? Here the +1. Think like this. Here the +1. -8. So what is the net difference? +1 -8. Net difference is -7, right? -7. So in order to make a 0, here the net excess charge is -7 because here is +1 and there is -8. The net excess charge is -7. In order to make it 0, your manganese should have offer +7 because the net excess charge is -7. Then your manganese should offer +7. Then only it becomes 0. Right. Yeah. Okay. I'll give you one more example. Listen. If I have K2Cr2O7. Okay. And you're asked to find the oxidation state of chromium. So put it as X. So the first idea. Sum of oxidation state will be 0. Oxidation state of potassium, that is +1 into 2, plus oxidation state of chromium, let it be X into number of chromium, that is 2, plus oxidation state of oxygen, that is -2 into number of oxygen, 7, that is equal to 0. So 2 plus 2x minus 14 equal to 0. So 2x is equal to +12 implies that x is equal to +6, right? Yeah. X is equal to +6. Is it okay? Or in another sense, K2 Cr2O7 split into 3, right? So here minus 14 because 7 oxygen can offer minus 14, 7 into minus 2. But you know, here plus 2 because 2 potassium can offer plus 2. So here plus 2, the minus 14. So what is the net difference? Plus 2 minus 14, minus 12. That minus 12 should be balanced by chromium. So chromium part should offer plus 12. That means, right, is it okay? Is it okay? Here plus 2, the minus 14. So that net difference is minus 12. That minus 12 should be balanced by your chromium. So minus 12 balanced by chromium means chromium part should offer plus 12. But there is 2 chromium which have to offer plus 12. So 1 chromium should offer plus 6. Both answer are same. Okay, ready. One more logic is there. One more idea. That idea is about a polyatomic ion. Idea is about a polyatomic ion. Polyatomic ion. Listen. Sum of oxidation state of a polyatomic ion is the charge on ion. Sum of atomic state of a polyatomic ion is the charge on the ion. Listen, there are 2 types of polyatomic ions. Listen, let me have PO4 3-. This is a polyatomic anion. Polyatomic means something having more than 1 atoms. So atoms are phosphorus and oxygen. So this is a polyatomic, but it's an anion, polyatomic anion. We have another one, NH4 plus. This is a polyatomic cation, nitrogen, hydrogen. These 2 are 2 different atoms. So more than 1 atom, polyatomic, but it is a cation. And the sum of oxidation state of a polyatomic ion. In the case of a neutral molecule, sum of oxidation state will be 0, right? Yeah. But the sum of oxidation state of a polyatomic ion will be the charge on the ion. What is the charge mentioned on that ion? That will be the sum of oxidation state. The charge mentioned is -3. So the sum of oxidation state of phosphorus and oxygen will be equal to -3. But here the charge mentioned is +1. The sum of oxidation state of nitrogen and hydrogen will be equal to +1, right? Is it okay? Yeah. So you are asked to find the oxidation state of phosphorus. Now here asked to find the oxidation state of nitrogen. How we can find this? Simply put it as X. Then tell me. X into 1. X is oxidation state of phosphorus into number of phosphorus is 1. Plus. What about the oxidation state of oxygen? -2. -2 into 4. Which is not equal to 0 because this is not a polyatomic, this is not a neutral molecule. This is a polyatomic ion. Then the sum of oxidation state of that polyatomic ion will be the charge on the ion. The charge on the ion is -3. So this is not equal to 0. This is equal to -3. Is it okay? Yes. X -8 equal to -3. So X is equal to +5. Right? Yeah. And what about the alternate method? PO4 3-. Second method, you split it into 2. Okay? Oh, into 3. Here, 4 oxygen. 4 oxygen -8. 4 oxygen -8. 4 oxygen -8. Okay, what is the net difference? 4 oxygen -8. And this is something like equal to, right? This is not the charge. It is a total charge. So this -8 and this -3 can be finished. So the net value will be -5. Here the charge is -8, but it already having a net charge of -3. So you simply cut that charge. -8, -3. So -3 from both. So there exists a remaining charge of -5. So phosphorus have to offer +5. The idea? Yeah, it's both are same. What about ammonium? Ammonium ion, NH4 plus. You are asked to find the oxidation state of nitrogen. So put it as X. So X into 1 plus. What about the oxidation state of hydrogen? That is +1 because hydrogen with the non-metal having +1 charge. It is defined into 4. And this is equal to +1, right? Because the total charge of that species is +1. So X plus 4 equal to +1. X is equal to -3. Or the next alternate idea is we have NH4 plus. NH4 plus. And you split this into 2. So we know the charge of hydrogen. Hydrogen should offer +4 because one hydrogen have +1 and the 4 hydrogen have +4. Here the +4 and the total is +1. Total +1 means 1 means +1. So the remaining charge here already have +4, but the total is +1. So the remaining charge, you cut this. The remaining charge is +3. Ready? So here will be -3. That's the idea. -3. Or you can find it in any way, either by putting X or by your own idea. Okay? But you have to know that, or you have to find that. Or you should find the unknown oxidation state of any case. Because we already discussed the complete rules for the oxidation state of different elements. Okay? We'll do a lot of problems regarding the finding the oxidation state of elements. Let's do it in the next part.